Very well, friends. Section 4.2 of Venema's Foundation of Geometry deals with triangle congruence conditions. That's what we're going to look at, triangle congruence conditions. There's only one that we know of. There's only one that we know of. And that's the side angle side condition. In the side angle side condition, I've got triangle blue and triangle black and triangle red, triangle black and triangle red, and they're marked up in such a way that BL is congruent to RE and LK is congruent to ED and angle L is congruent to angle E. And so we have postulated that those triangles are congruent. But that's not the only way to get triangle congruence. There are other ways. I would like to share one with you. I would like to share several with you. And so I'm going to, because I can. So this is triangle ABC, and this is triangle DEF. And we're going to mark them up so that angle A is congruent to angle D, and angle B is congruent to angle E, and AB is congruent to DE. And we're going to call this angle side angle, because guess what? Two angles and the side in between them. Two angles and the side in between them. So here's the thing. If this happens, is this just as good as side angle side? That's the question. Is this just as good as side angle side? Well, to get side angle side, we need another side. And so the way we're going to do this is we're going to generate that other side. We are going to pick a point. We're going to take ray AC. We're going to say there is some point on ray AC, call it C prime, right there, such that AC prime is congruent to DF. We're going to pick a point, call it C prime. It has to exist. The ruler postulate says it has to exist. DF has a length. Ray AC is infinite in length, so there's some point C prime where the distance between A and C prime is the same as the distance between D and F. We are going to generate that point. Maybe that point is C. If it is, we're done. So here's my contention. My contention is that triangle C prime AB is congruent to triangle FDE. Those triangles are congruent by side angle side. And if those triangles are congruent by side angle side, and remember those, that's this. That's the red triangle congruent to the other black triangle. So now what does that mean? That means by corresponding parts, angle, angle C prime BA is congruent to angle FED. Angle C prime BA, that's this angle right here, is congruent to angle FED. But wait a second. Angle CBA was congruent to angle FED. So angle C prime BA is congruent to angle CBA. Now that's not really a problem, is it? Oh wait, yes it is. That's a problem. Because C and C prime are on the same side of AB. And the protractor postulate says there's only one ray on one particular half plane bounded by AB such that angle AB whatever is a given measurement. Therefore, C prime is C. And so a triangle ABC is congruent to triangle DEF. So if you have angle side angle, that is just as good as if you have side angle side. It's just as good. So if you can get angle side angle and you can't get side angle side, doesn't matter, just as well. Hey, while we're on the topic of things that should be proven, consider the following. Let's pretend that you have a triangle, triangle ABC, and those two angles are congruent. In triangle ABC, if angle ABC is congruent to angle ACB, then I claim AB is congruent to AC. This is one of those proofs that I'm going to leave to you because I think you can do it. It looks very, very similar to another proof that we did involving isosceles triangles. This is the flip side of the isosceles triangle theorem. Okay, back to triangle congruence. Let's hit angle, angle, side. In angle, angle, side, I have two triangles, triangle ABC and triangle DEF. I've got two angles and a non-included side. So I've got an angle and an angle, an angle and an angle, and I've got one of the other sides. I don't have BC congruent to EF. I've got one of those other sides like so. So that's the way it's marked up, angle, angle, side. We will walk through this in class. I will walk through why this is just as good as side angle side. If you have angle angle side, it's just as good. We actually generate angle side angle, and that turns out to be A-OK. We'll do it by picking a point on BC. We'll call it B prime. We're going to prove some things about triangle AB prime C as it compares to DEF. We're going to take a look. We're going to say that B prime C is the same as EF by construction, and we're going to prove some things based on that. So that's the shell. That's where we're going. Angle, angle, side is just as good. Well, while we're putting combinations of angles and sides together, why not side, side angle? What could be so bad about side, side angle? Well, consider the following picture. Got, let's see, we'll pick a four-letter mathy word. And let's pretend that MH is congruent to MT. I maintain that triangle red should be congruent to triangle blue by side, side angle. I maintain that. And I think that's pretty easy to show because this side is congruent to itself and this angle is congruent to itself. So in the red triangle, I've got MA, MT, and angle A. In the blue triangle, I've got MA, MH, and angle A. Those two triangles should be congruent, but guess what? They're not. Turns out that if that happens, this angle and that angle are either congruent or supplementary. That is a significant result. Those angles are either congruent or supplementary, and I think it'll be easy for you to prove that they're supplementary once I do that right there. That should be an easy proof for you. But side-side angle does work in the case where congruent does mean supplementary, and that's your right triangle hypotenuse leg congruence. If I have a right triangle ABC and a right triangle DEF, right angles at C and F, and AB is congruent to DE, and either of the other legs match, angle side side does work. Now in high school, we do this by invoking the Pythagorean theorem. We say, hey, wait a second, Pythagorean theorem means that the third sides are going to match, and so we get side angle side just like we wanted. That is not the case here. We don't have the Pythagorean theorem in neutral geometry, and so we actually have to do some serious hand waving on this one, some serious hand waving. So here's what we're going to do. We're going to extend ray AC. We're going to extend it as far as we can, and we're going to pick a point. I'm going to call it D prime, so that CD prime is as big as DF is. We're going to pick it. Well, we know that's a right angle, and BC is the same as EF. So green triangle, BCD prime, is congruent to EFD. Those triangles are congruent by side angle side, which means that ED is as long as BD prime. Those are congruent. They're corresponding parts of congruent triangles. Well, guess what, folks? That means that if BD prime is congruent to BA, then in isosceles triangle BAD, this angle is congruent to that one. And now I have angle, angle, side congruent to angle, angle, side. So right triangle hypotenuse leg works even in hyperbolic geometry because it is based on the axioms of neutral. Kind of weird, huh? You didn't think about that. Hey, speaking of kind of weird, a theorem for you to prove when we get together. Here's a theorem for you. If triangle ABC is a triangle, DE is a segment such that DE is congruent to AB, and H is a half plane bounded by line DE, then there is a unique point F in H such that triangle DEF is congruent to triangle ABC. And this is one of those crazy things. I think there's a bunch of ways to prove it. We're going to figure out when we get to class. Let's pretend that there is some triangle ABC. It exists. And I get some segment over here, DE, and it's congruent to AB. What this particular theorem says is that there is a unique point in this half plane. There is also a unique point in this half plane. There is a unique point in each half plane such that if you connect the dots, triangle ABC and triangle DEF are congruent. We're actually going to construct this. When we get to class, it's an interesting thing for you to think about. Well, you're saying, wait a second, we missed one, and we missed the most obvious one. We missed side, side, side. I mean, what happens if those match up with those? How do you get side, angle, side, or one of the equivalents out of that? Well, interesting that you should ask that. Here's the way this goes. Side, side, side is the most intuitive, and yet Venema's proof is really, really convoluted. Not that it's bad mathematically, it just involves a lot of cases. There's a lot of geometry that goes into it. I'm going to hold off on the proof of side, side, side. I mean, you can read Venema's proof, and that's fine. Because I prove side, side, side using the hinge theorem, and we don't see the hinge theorem until the next section. Once we prove the hinge theorem is going to guarantee that this angle and that angle have to be congruent because this side and that side are congruent. Hinge theorem is going to give that to us. And once the hinge theorem gives that to us, side, side, side just falls right out. Okay, so that's just something for you to think about between now and when we gather. Glad you were along for the ride. See you next time.